Imagine this. You drop a ball and it falls to the ground. You rewind the video and it goes back up. Simple, right? Time seems to have a clear direction forward. But in physics, especially when you go down to the atomic level, things start to look strange. The laws that govern those tiny particles don't really care which way time runs. Forward or backward, the equations still work. This is where Richard Feynman stumbled upon something so deep, so paradoxical, that it helped him win a Nobel Prize. It's called the time paradox of quantum electrodynamics, or QED. To understand it, let's start with the problem. In the early days of quantum mechanics, physicists were trying to describe how light and matter interact. How does an electron absorb or emit a photon? How do these exchanges happen in the subatomic world? The equations that described them kept blowing up, giving infinite answers that made no sense. Imagine trying to measure the distance between 2 points and your ruler keeps stretching to infinity. That was physics in the 1930s and 40s. Even the greatest minds, Dirac, Heisenberg, even Einstein, were puzzled. Then came Feynman. He had this unique way of thinking, like a curious child who asks why the simplest thing happens. Instead of following traditional mathematics, he started to visualize particles like actors in a play. An electron could go forward in time, interact with light, and continue. But what if, he thought, the same electron could also move backward in time? That was the seed of the time paradox. In Feynman's picture, a positron, the antimatter twin of an electron, was simply an electron traveling backward in time. Let that sink in. Antimatter, the mysterious mirror version of everything we see, might just be ordinary matter moving in reverse through time. Now, this wasn't just a poetic metaphor. It actually made the math work. When Feynman flipped time around, the infinities that had haunted physicists disappeared. The equations began to behave. Suddenly, every interaction between light and matter could be represented as a series of tiny arrows and lines, what we now call Feynman diagrams. These diagrams didn't just simplify quantum electrodynamics, they transformed it into a visual language. Physicists could now see time bending, particles exchanging photons, and even virtual particles popping in and out of existence, all in a single sketch. But what does this mean for our understanding of time? If an electron can move backward, what does forward even mean? Is time just a direction we happen to experience? Here's a thought experiment. Imagine you're watching two mirrors facing each other, with a beam of light bouncing endlessly between them. From your point of view, the light is moving forward. But what if you reverse time? The light still bounces between the mirrors, perfectly consistent with physics. The equations describing those reflections remain unchanged. The only thing that changes is your perception, the arrow of time you assign to the process. At the quantum level, time isn't as strict as we think. The distinction between past and future fades. What we perceive as cause and effect starts to blur. And yet, in our everyday world, time feels irreversible. You can scramble an egg, but you can't unscramble it. Ice melts, but it doesn't unmelt on its own. So where does that directionality come from if the laws of physics don't require it? The answer lies in probability and entropy, the measure of disorder. Nature prefers states with higher disorder because they're simply more probable. When an egg breaks, there are countless ways for the molecules to scatter, but only one precise way for them to return. So while quantum laws allow time symmetry, the large-scale world we inhabit is dominated by the overwhelming odds of disorder increasing. That's the arrow of time, born not from the laws of physics, but from the statistics of the universe. Feynman understood this intuitively. In his view, time was not a rigid one-way street, but a flexible framework where particles could dance in both directions. This perspective wasn't just philosophically interesting, it was scientifically powerful. It led him to a complete reformulation of quantum electrodynamics that matched experiments with breathtaking precision, accurate to 1 part in a billion. That precision earned him the Nobel Prize. But what's truly fascinating is what this says about reality itself. If the future and the past are treated equally in the laws of physics, then our sense of now might be an illusion. Just one frame in a vast cosmic movie that already exists, start to finish. In that view, the universe isn't unfolding moment by moment. It's already there, timeless and complete. What we call time might just be the way our consciousness moves through that static structure. Feynman used to say that nature's imagination is far greater than ours. And he was right. The universe doesn't seem to care about the direction of time, yet somehow, within it, we evolved creatures who feel its flow. Maybe that's because consciousness itself depends on memory, on change, on an arrow pointing forward. Without it, life as we know it wouldn't make sense. Still, there's something beautiful about realizing that, in a deeper sense, everything that has ever happened and ever will happen might coexist in one timeless fabric. The electron going forward in time and the positron going backward are two sides of the same coin, like reflections in a mirror. Our lives, our choices, our history, all might be threads woven into that fabric, eternal and unchanging. Feynman never tried to turn this into mysticism. He just followed the logic of the equations and marveled at what they implied. To him, the mystery wasn't something to solve, it was something to appreciate. He once said, "I think it's much more interesting to live not knowing than to have answers which might be wrong." And that's perhaps the truest lesson of the time paradox, that the universe at its core doesn't obey our human sense of direction or order. It simply is. So the next time you look at your watch ticking, or you see the sun setting, remember in the deepest laws of physics, time doesn't flow, it just exists. Forward, backward, all at once, what we call the present, is simply where we happen to stand in that grand, timeless dance of particles. And maybe, just maybe, understanding that helps us see the universe, not as something passing us by, but as something we're eternally part of, woven into its quantum tapestry, existing forever, both forward and backward in time. The illusion of time. You drop a ball and it falls. You rewind the video and it rises again. To us, one feels natural, the other absurd. Time, we believe, always moves forward. But here's the twist. The laws of physics don't agree with us. Down at the atomic level, nature doesn't seem to care which way time flows. Whether it's forward or backward, the equations work perfectly. The symmetry is astonishing. And that's where a young Richard Feynman, curious as ever, began to question something so simple that everyone else had taken it for granted. What if the arrow of time, this one-way direction we experience, isn't fundamental at all? What if deep down particles live in a timeless world? In the 1930s and 40s, physicists were trying to understand how light interacts with matter. How do electrons and photons exchange energy? The equations describing these processes were giving nonsensical answers, infinite values, mathematical explosions. The greatest minds were stuck. Then Feynman came along and decided to rethink the entire picture. Not with heavier math, but with imagination. He asked a question that no one else dared to take seriously. What if an electron could move backward in time? When electrons travel backward, imagine an electron moving through space and time, emitting a photon, a particle of light, and continuing forward. That's normal physics. But Feynman noticed something odd when he flipped the direction of time in his equations. Suddenly, that same electron could be reinterpreted as something else entirely, a positron, the antimatter version of the electron, traveling backward through time. It wasn't science fiction. The math worked. Perfectly. Antimatter, which had just been discovered, was one of the strangest things in physics. When matter and antimatter meet, they annihilate each other, turning into pure energy. But what Feynman proposed was deeper. Perhaps antimatter wasn't a separate thing at all, just matter seen from the other side of time's mirror. In his picture, an electron could zigzag forward and backward in time, creating the illusion of multiple particles popping in and out of existence. This became the foundation of a new way to describe reality, not as static points in space, but as histories, as paths through time itself. Every particle, every event wasn't fixed. It was part of an endless network of possibilities, some moving forward, some backward, all contributing to the outcome we observe. This idea, wild as it sounded, didn't just explain antimatter. It fixed the infinities that plagued quantum electrodynamics, the diagrams that changed physics. Feynman didn't stop at equations. He turned these abstract ideas into something visual, something any physicist could draw. Little arrows, loops, and lines, diagrams that showed how particles interact. Each line represented a particle's journey through space and time. When two lines met, it meant they exchanged energy, perhaps a photon of light. These Feynman diagrams were more than drawings. They were maps of reality. They turned impossible calculations into something simple and intuitive. With them, you could predict how an electron would scatter light, how atoms would form, even how stars might burn. For the first time, quantum electrodynamics, QED, made sense. It became one of the most precise theories ever created. Predictions based on Feynman's methods matched experiments to an accuracy of 1 part in a billion. That's like measuring the distance between New York and Los Angeles and being off by the width of a human hair. And behind all that precision was a time paradox, the idea that particles don't just move forward, but can dance backward through the timeline, creating a perfectly balanced picture of cause and effect. Part 4, what time really means. But what does it mean for something to move backward in time? Doesn't that break causality, the idea that cause comes before effect? Here's the strange part in quantum physics: causality isn't broken. It's redefined. At the microscopic level, particles don't obey strict sequences. They exist in a superposition of possibilities. What looks like randomness is actually nature exploring every possible history at once. Think of a light beam bouncing between two mirrors. If you film it and play it in reverse, the reflection looks exactly the same. The laws of physics don't care whether time is running forward or backward. The only thing that changes is our perception of direction. So, why, then, do we experience time as one way? Why can you remember the past but not the future? The answer isn't in quantum mechanics but in entropy, the measure of disorder. Systems naturally evolve from order to disorder simply because there are more ways to be disordered. When an egg breaks, there are millions of ways for the shell to scatter, but only one way for it to be whole again. That's why we experience time as moving forward, not because of the laws of nature, but because of probability. At the quantum level, time symmetry reigns. But in the macroscopic world, the one we live in, the arrow of time emerges from sheer statistical inevitability. The eternal dance of time. Feynman's insight reshaped not only physics, but our understanding of reality itself. If an electron moving backward in time is indistinguishable from a positron moving forward, then perhaps time is not a river flowing from past to future. Maybe it's a vast ocean, still, complete, and timeless, and what we call motion, or change, is simply our consciousness moving through it. In that picture, the universe doesn't unfold. It already exists, past, present, and future all at once, a cosmic film reel where every frame is already printed. We just happen to be watching it one moment at a time. Feynman never turned this into mysticism. He didn't claim to have final answers. He simply accepted that reality is stranger than our intuitions allow. As he once said, "It is impossible to find an answer which someday will not be found to be wrong." He embraced the mystery, not as something to conquer, but to appreciate. And maybe that's the real lesson of the time paradox, that our universe doesn't need our sense of direction or purpose to be beautiful. It just is. So the next time you watch a sunset, or see your reflection in a mirror, remember somewhere in the quiet mathematics of the universe, an electron is dancing backward in time. And in that tiny, elegant reversal lies one of the greatest insights ever discovered, the realization that time itself might just be nature's most beautiful illusion. Would you like me to make it slightly more cinematic and conversational, or keep this literary and narrative style? The mirror of time. When Richard Feynman first drew those strange little arrows, the ones representing particles zipping forward and backward through time, he wasn't just solving a physics problem. He was revealing a truth about nature that touches something far beyond equations. We like to think of time as a current, carrying us from the past into the unknown future. Our lives are built around that assumption. We remember what came before, we anticipate what's to come, and we call the thin slice between them the present. But Feynman's work whispers something quietly revolutionary. Perhaps time doesn't flow at all. Perhaps everything, every birth, every death, every breath, every beam of starlight already exists spread out in a grand, timeless pattern. If that's true, then what we call the passage of time might be an illusion created by our consciousness, like the way a film reel holds every frame at once, but we only see them in motion when the projector runs. The universe, then, could be a kind of four-dimensional film, a block of space-time, and we are the audience watching it unfold frame by frame. This idea isn't just philosophy, it's embedded in the mathematics of physics itself. Einstein's theory of relativity already tells us that past, present, and future are woven together into one fabric. Feynman's quantum insights only deepened that picture, showing that even the tiniest particles don't obey our human sense of direction. They move both ways, dancing along the threads of time's fabric, connecting what we call before and after, in ways we can barely comprehend. But here's the real paradox. If the future already exists, does that mean we're trapped within it? Are our choices meaningless? Feynman would have smiled at that question and shrugged. He wasn't interested in turning the mystery into fate. He believed that understanding doesn't destroy wonder, it multiplies it. He might have said the future may exist, yes, but that doesn't mean it's known to us. We are explorers within the tapestry, discovering what's already there, and in doing so, giving it meaning. Our choices still matter, not because they change what is, but because they reveal who we are within the vastness of what's possible. Think about what this means for how we see reality. The universe isn't just ticking like a clock, moving towards some destination. It's eternal, existing all at once, with every heartbeat, every star, every whisper of light fixed in a cosmic geometry of existence. We are not travelers through time, we are structures within it. Every thought, every action, every atom is a point in that structure, part of the same eternal whole. And yet, in our limited perspective, we experience it as a story with beginnings and endings, memories and hopes. That story is precious precisely because it feels fleeting. Time gives life its flavor, its urgency, its beauty. The fact that we can only move forward, only remember the past and not the future, makes existence meaningful to us. Without that asymmetry, consciousness might lose its narrative. Feynman's time paradox doesn't destroy the meaning of life. It reframes it. It reminds us that even in a universe governed by perfect symmetry, imperfection, the human experience of time, is what gives rise to curiosity, emotion, and wonder. So maybe the real magic of the universe isn't that time exists, but that we feel it, that we get to live inside the illusion and call it no. And maybe, when we look up at the night sky and see starlight that's traveled for millions of years, we're not looking into the past at all, but across the timeless structure of reality itself. The stars aren't gone, they're still there, written into the geometry of the cosmos, as eternal as the particles Feynman once imagined moving backward through time. He taught us that the beauty of science isn't in the certainty of answers, but in the wonder of the questions that remain. The time paradox that helped him win a Nobel Prize wasn't just about subatomic particles. It was about redefining what it means to exist in a universe where time, direction, and cause are not what they seem. And in that realization lies a quiet kind of awe, that maybe the past is still here, the future already written, and we, like Feynman's particles, are simply moving through a timeless sea, forever dancing in the echo of the universe's most profound mystery.